Hello everyone, welcome to session number 10 of the Printed Circuit Board Design Principles and Practices. In our today's session, we will go over some important topic to create a professional design, as quite complex design, Altium Designer, especially when it comes to a flat hierarchical design and multi-sheet also design. In addition, we will look into different tools and different type of net classes, and also we'll look into the cross-propping and cross-selecting. So starting with two important definitions in Altium Designer, a physical connection and logical connection. So basically, on a schematic design, you can create connectivity by drawing a wire from one component, in this case, this resistor, all the way to the other component or the pin of the other component. Like here we have I/O for a microcontroller. And this is referred as physical connectivity because you have physical connection between the two components or the pins of the two components. On the other hand, you can connect one pin to another by drawing small wire and adding a net label on that wire and then another net label on the other component. And now when you compile the design, the software identifies these two net sections and connect them to form a single net. And this type of connectivity is referred to as logical connectivity. In general, physical connectivity allows a reader to follow each wire as they study the circuit. As you can see in here, if you have now this is switching between physical and logical connectivity. But physical connectivity, you can see where each wire is going from point A to point B. But as the design gets more complicated, a lot of wires will result in a dense and busy schematic sheet, and it will be very hard to read and to track these wires going between different components. On the other hand, net labels reduces the amount of wiring, but instead the reader must scan the sheet to find all potential connections. As a designer, you are free to decide which connectivity model best suits your design, including a mixture of both techniques. Now, in Altium Designer, we have a set of net identifiers, and these net identifiers are used in the schematic editor to create connectivity. And these are the net labels: power ports, off-sheet connector, sheet entry, bus entry, and signal harnesses. Now, starting with net labels, as you can see in here, these are net label SW1, 2, 3, 4. These from their name, it's just net label. It's labeling, giving a meaningful name for a net. And these kind of identifier used to create a connectivity to other net label with the same name on the same schematic sheet. So the important point in here, they connect other wires with the same name on the same schematic sheet. And these nets are automatically named by the net label text. When you compile the project or you compile the design, these nets will automatically named according to the net label. And this net label can be placed on component pins, wires, and buses. So again, net labels are dedicated for connecting wires within the same schematic sheet. They are not meant to connect wires and nets between two separate schematic sheets, unless you change the net identifier scope to global, as we will see that later on. But you don't want to really do that. So the second identifier or object is the power port here. These are different type of power ports, as you can see. So the ground port or the VCC port or the VDD ports, all these are different type of power ports, and these are global. They have global level. meaning if you place them on any sheet, all of them will be connected together as long as they have the same name. So if you name GND board, power board as GND or ground, and then you copy this and use it on a different schematic sheet, all of them will be connected internally and automatically once you compile the design. And they don't look at the structure you are using, it's global or local, it doesn't matter. Power board, they have their own characteristic and they connect everything with the same name. So even if the symbol is different but the name is the same for the power board, they still connect. So the property the software will try to connect these power boards is the name of the power board. And let's take a look at Altium Designer just to make it clear. Let's open a project of the samples project in Altium Designer. This is local Altium Designer 19 example. Let's open the PCB. Let's open the memory. So let's look at this sheet. And this is the second sheet. We'll talk in a minute about this flat design. So here we have a power board, and we can see all the different power boards in here, as you can see. Now this power board has a ground. Now if I take this one, and it has the same name, it's also ground. And these, if I connect this one for instance here, now once I combine the project in here, these two nets now are connected. This one and this one, they are connected together. Basically, I'm shorting this pin to the ground because they have the same name. Now, if I change this name into what, let's say GND, now this is totally different power board now because it has a different name. They are not connected together, and you can see that you have now here we have a color identification. If you move this one a little bit, you will see the color changing in here. Now let's change this one to ground and remove this label. As you can see, it's the same net now. Now if I change this one, you know that from the color, if I change this to analog ground, it's totally different name. So let's reverse back to the original design. We are doing that just for representation. So okay, so this is for the power boards. As for the boards, these are the boards. They are used to connect a net from one schematic sheet to another schematic sheet. So if we go back to Altium Designer in here, so here we have one schematic sheet, and they are not using board on this one to connect sheets together. But let's open a different example. Let's open mini board, motherboard. Okay, so this one is basically, this one is vertical design and this one is horizontal design. If we look at, for instance, this sheet, so here you can see these are boards, but let's see if we can find simple boards, not harnesses. Anyone? Okay. Okay, so these are harnesses, but it's the same thing. They are boards, and these are used to connect different schematic sheets, this one with this one, and you can see that from the top level sheet. As you can see in here, these are boards. Now the connectivity using the boards can be vertical in hierarchical design, or it can be horizontal in flat design. We'll see that also in the next coming slides. Now the name of the board can be used to name the net as well. So if we go back to Altium Designer, if we add, for instance, a board in here, this is a board, and then if you click on it, you will see the properties of this board, and this is the name of the board. So let's say this one is UART TX, for instance, and this one is, you can select the directionality or the type of it, it's output, and if you connect this port with any net, it will change the name of that net. So let's take it to a place where we can connect it with a line. So let's assume that this one is in here, and now if you connect this one with this, now the line of this net will change based on the port. So it's just we should not do that because this one has a name, but it's just for representation. Now the other net identifier is the off-sheet connector, and off-sheet connector, these are off-sheet connectors in here. As you can see, we have 3 off-sheet connector: interrupt, serial data, and serial clock. And these are used to connect a net from one sheet to another sheet, not within the same sheet. So also it's between 2 sheets. So what is the difference between port and off-sheet connector? Because both of them are used to connect nets between 2 different schematic sheets. Basically, in the short answer is off-sheet connector are used when you do a flat design. Boards are more into hierarchical design, and also we'll see that in a minute. We'll simplify it, but here we are just presenting different type of net identifiers. Now, sheet entry, and this is a kind also of hierarchical design or vertical. So when you hear that term horizontal or flat, meaning you have a flat design, you have multiple schematic sheets, but they have a flat design. You don't have a main sheet that link all of them together. You don't have hierarchy at all. So when you hear the term vertical or hierarchical, that means you have hierarchy, and you have a parent, you have children's, and so on. And we will see that in a minute. So no worries about that. So sheet entry, this is the sheet entry as you can see in here. This is the entry, and this is a sheet symbol. This is the entry, sheet entry, and it's placed within a sheet symbol. This is the green one, is a sheet symbol, to create a connectivity to a port of the same name on that sheet symbol's child sheet. So this port is basically used inside this schematic sheet that is referenced to this sheet symbol, and this sheet entry connects with the internal board, and then it connects with the other board on another sheet through also sheet entry. And we will let's do quick representation for that, or we have example here we can show. So here everything is buses. We can create something here very quick. So if we add sheet entry in here, before we do that we need to add sheet symbol. If we had sheet symbol, and we have another sheet symbol in here, and then we need to add sheet entry. For this we have here, and then we have sheet entry in here. Now let's name this one as txd, and name this one as also txd. It's okay. Now if we connect these two together, and now we have boards inside this. There is a schematic sheet links to this, and there is a schematic sheet links also to this sheet symbol, and now they are connecting through these sheet entries. Now we'll build the whole project in a minute, so this is just a quick representation for that. So buses, it's basically used to bundle a set of nets. As you can see here, this is a bus. This thick wire here, you can see it is a bus, and this bus is bundling 8 wires, SW0 all the way to SW7. And buses are very useful when you have, especially when you do memories, parallel memories, and you have data buses, and where you have like a 16-bit data bus, or you have 24-bit data bus, or control bus, or address bus. So they are very useful to simplify the schematic design. The bus entry is basically similar to the board, as you can see in here. This is a bus entry. It's similar to the board, but it's called, but you can call it bus board or port or bus entry. And basically, it's graphical representation, nothing more. You don't have to put it because we count on the label on the bus rather than counting on the bus entry, but it's just a graphical representation, an extra graphical representation. Now the last one is signal harness. This is the signal harness, and signal harness used to bundle any combination of nets, buses, and lower level signal harnesses as well. So buses only you are bundling nets. In signal harness, you can bundle bus, you can bundle nets, you can bundle different combination of both. And we will learn to use all of these net identifiers today. Before we start using these net identifier, we need to explain the difference between flat and hierarchical design. Now, if the design does fit into a single schematic sheet, it can be compiled as a single schematic sheet. No worries, my design is very simple. I don't need multiple schematic sheets. Everything can fit within one schematic sheet. But if we look at a design similar to this, here where you have where you are designing a motherboard, mini board for FPGA, with so many components, and every single sheet of these is like hundreds of components. Let's take a look, for instance, for this memory. So you cannot fit all this design. We have so many schematic sheets on one sheet. It's gonna be huge, even if you use a big sheet, and it's very difficult to reuse the component or to track the connectivity between the component or understand the architecture of that system. So in this case, you need to divide your design into multiple schematic sheets. And there are two distinct models for organizing and creating connectivity in multiple schematic sheets, either as a flat design, which is what you see on this schematic sheet or this slide, or as hierarchical design, as you can see on this slide, and we will talk about each one. For flat design, or sometimes they call it horizontal structure or horizontal model, basically you can think of a flat design as if a large schematic sheet has been cut up into a number of smaller sheets here. So you have a huge schematic sheets, and you are dividing the elements in this schematic sheet into multiple sheets to fit all of them on different sheets and make the design simpler. But as you can see in here, you have 1, 2, 3, 4 schematic sheets, one for the LCD, one for the microcontroller, one for the power regulation and distribution, and one for the sensors. Now, what is good about this here, when you have something divided into multiple sheets, you know that the functionality of LCD or the design for LCD exists on this schematic sheets. Now you have a kind of module dedicated for a specific hardware. In the future, if you want to reuse this module, you just copy this schematic sheet and add it into a new project. Basically reuse or reusability. So all schematic sheets are on the same level. You don't see a parent in here. All of them are on the same level. You have 4 schematic sheets on the same level, and the connectivity in flat design is created directly from one schematic sheet to another through the ports or off-sheet connectors. So we can use either ports or off-sheet connectors, as you can see in here. And this is the reason why they sometimes call it, this structure is called as horizontal connectivity. Now, in some cases, they might use a top sheet. like in here. So you have a top sheet, but there is no connectivity or ports on the top sheets. Once you add a connectivity on the top sheets and ports, now you are switching from flat design into hierarchical design. But if you want to add the top sheets, that's fine. But there should be no ports or connections on the top sheets, and all your sheets is still connecting directly from one sheet to another through ports or off sheet connector. So this is both of them are flat design, and here you don't have a top sheet, and here you can see you have a top sheet in here, which is the first one. So you have 4 green blocks. Just will tell you, okay, you have MCU sheet, you have sensor sheet, you have bar sheet, and you have LCD sheet. But there is no architecture in here. You don't know how they are connecting, and there are no ports at all. So the next type is the hierarchical design or the vertical architecture. And here, as you can see, you will see parents and children's type of hierarchy. And in this type of hierarchy, you need to use sheet symbols. As you can see, these are the green ones, to determine the parent to child relationship created by the sheet symbols and sheet entries as well here. So you know that this is connecting with this and this and that through these ports, and these are the name of the nets, and then this one connect with that, and the flow is always from the left all the way to the right. So you need to make sure when you design this type of hierarchy, the flow of data or components is from the left side all the way to the right side. So again, in hierarchical design, a signal on a child sheet, as you can see in here, leaves the sheet via a port. So you can see here we have a port, and then connect upward to a matching sheet entry on the parent sheet. And the parent sheet includes wiring that carries the signal across the sheet entry in another sheet symbol, as you can see in here. So this is one schematic sheet, and this is another schematic sheet, and the nets in this schematic and that schematic are connected through ports, and this ports is referenced through a sheet entry which has the same name of the board, and now you are transferring this net to the other schematic sheet, from one schematic sheet to another schematic sheet through a wire connecting the sheet entries on the first sheet symbol to another sheet symbol. It's basic, and we are going to implement that. And this is the structure now. This is the top sheet, and then you have left sheet and you have right sheet in here. 3 schematic sheets. Let's do this example to simplify the understanding of this process. So let's create a project, just empty project. Let's close this. Let's add schematic sheet to this, and another schematic sheet, and another schematic sheet. Now we need to add sheet symbol. We need another one. Now let's call this one right, and this one designator left, and then let's add sheet entry on this and on that. And now let's call this one whatever P R, and this one is P left, and let's say this is bidirectional connection. And now we need to save the project. Okay, file. Save. Let's save it in here. Sheet 5 and sheet 6. So sheet 4 is the parent because we have everything on sheet 4, and then we have sheet 5, we need to have a port in here, and I think we called, let's put just a power pin, connect this one to the ground, doesn't matter, and we call this one, I think, PR, and we can copy this and go to the 6, and we call this as PL, and this one is bidirectional, and the other one is also bidirectional. We can save this, and we can save this, and now all that we need to do is to connect this with that. So let's close. Let's name these sheets just to make it simple. You can name them by going to the storage manager. And the storage manager. So sheet number 4, let's call this parent. And sheet number 5, let's call this child 1. And this one, let's call it child 2. And you can see them changed now. Let's save everything. Now we double click on this. We need to assign child 1, and this one we can assign child 2 to it. Now look how the hierarchy will change right now when I compile it. You can see this is the parent, and this is child 1, and this is child 2. And now they are connected together. If we put them window vertically, we can hide this. So basically this is the PR, this is the board in here, PR, and it's going into the sheet entry in here, and this is the board PL is connecting with this one, and now they are connecting externally over the sheet entries in here. And now we know that this port on this sheet is connected with this port on this sheet as well. They are connected together to the same net. So one thing you can do, you don't have to create these ports. Basically, if you connect from here to here, and it will take the same name, but you need to change now the name to the name of the net inside. If they have the same net name, they will connect together. This is just a quick example how you can create hierarchy, and this is you can see you have parent and you have children's in here. This is an example, and the same thing you can see it on this project on the mini PC. So you can see here you have parent and you have a children's underneath, and this is one level. You can create multiple levels. You can create as many levels as you want, and also you can create as many sheets as you want also. There is no limitation for that. So this is one level in here. Then you have another level in here. So now power, basically power schematic sheet is a child for mini PC function schematic sheet, but all these sub schematic sheet, they are children for the power schematic sheet. Same thing here. So this is a child for the mini PC function schematic sheet, but anything underneath this one, structured underneath this one, all these are children to this one. Now if you click on this power, let's close the other sheet that are open. Okay, so if you click on the power, now you see a new hierarchical design, and you can see all these sheet symbols that refer to a schematic design. Now if you hold Control down and double click on the sheet, on the symbol, it will bring up the associated schematic sheet design. And here you can see we have BCIE underscore EN, which is the board, BCIE underscore EN, as you can see in here. So it will show the board. So you can create as many levels as you want. So that's why sometimes they call the parent-child sheet structure can be defined at any depth. So in this case, in here, as we saw, we have the depth is 3 or 2. So this is 1, then 2, and this also still 2. It's not branching, but you can have 100 level on the depths. There is no limitation for that. And in addition to add like simplification, readability, and organization to the design, the other advantage of hierarchical design is that it provides a platform for a delivery of sophisticated design reuse system. Basically, when you divide your schematic design into sheets and each sheet refer to a specific circuit, now it's very easy to reuse these schematic sheets. For instance, if you need a 12 volt, 3.3 volt, and 1.8 volt switches, all that you need to do in the future is you just take a copy of this schematic sheet and reuse it in a different design. If you need an Ethernet interface, for instance, you didn't have to create this design from scratch. Basically, you can reuse this design in here. It's reusable. And now how you link this sheet with the other sheets on the design through these boards. This is what's good about it, because this is like a totally independent entity that can be reused in a different design. So let's go back to the slides. So here we can see, if we look at this, we can see this is a parent, and then we have a child, and under this child we have also two children. So this is one level or two levels, and then here you can see you have a child, and then another level underneath it. So it's a 3 level. As you can see, the first level is this, the second one is this, the third one is this. So you have 3 levels in this hierarchical design. One last point before we move in here, if you recall the net identifiers, as we said, the net labels are used to connect nets within the schematic sheet, the same schematic sheet. They are not meant to be used to connect nets with different schematic sheets. So if we go back to here, and this will explain that. So here, if we have a net C1, net C2, and you have also C1 and C2 on the other schematic sheet, they are not physically connected, neither logically connected. So you need to be very careful about it to name nets on one schematic sheet, and you are assuming that they will be connected with nets on the other schematic sheet using the net labels. No, they will not be connected unless you change the net identifier scope into global, and we will talk about that in the next slide. So for net identifier, meaning when you change it to global, that you are telling the design if you are using ports, if you are using off-sheet connector, if you are using net labels, it's okay to connect them together even if they are on a different schematic sheets or they are on totally different level. So let's talk about net identifier scope. So if you go to the settings for Altium Designer under the project options, and here you can see net identifier scope, and you have multiple options. The default option is automatic, and also you have a flat, hierarchical, and you have also global. So let's talk about these 3 options in a minute. So the first one is global connectivity. In a global connectivity, if you have children and parent, and you can connect any net from one schematic sheet to another schematic sheet via ports or net labels as well. All of them will work as long as you set it to global. Basically, net identifier scope is global, meaning you can use anything, any net. But now, where is the problem? If you have net label and you use the same net label on schematic sheet, on other schematic sheet where you should not do that, now everything will be connected and you will get a problem with that. Now the other one is the flat connectivity. When you have a flat design similar to this, flat design, you can have a top sheet, but there should be no ports or connecting on the top level sheet. It's like that. So you have 2 sheets, but they are connecting through ports directly from one schematic sheet to another schematic sheet. And in this configuration or this net identifier scope, the net labels on the first schematic sheet will not connect to the net labels on the second schematic sheet, even if they have the same name or the same designator, they will not connect. So what is good about this, if you have a schematic sheet A and you have schematic sheet B, you can use, you know that for sure the net labels on this schematic sheet will not connect with anything else, even if by mistake have the same net label. For instance, if you look at a design like that, it's highly complicated, and you can see here net labels all over the place, everywhere. Now, we know that for sure if we go to the project options and we look under the options in here and we look, it's hierarchical. So hierarchical meaning there is no way to connect between sheets except using the port connections. It's showing that in here. So you need to use sheet entry, board connections, and the board powers. As I said, the power boards are global. But if this one is a flat or not flat, is global, now you have a problem with that. If two sheets have the same connection, they will connect together. Once you combine the branches, will connect together. So for a complex project like that, you need to have it hierarchical of course. So as you can see, this is hierarchical. In here, you are using the boards to connect two schematic sheets together. So, and this is what I use all the time. Now, what about the other option, which is automatic? Let's take a look at here, which is the default when you create a new project and look at the net identifier scope, it's always on automatic. So it says based on the project contents. Basically, when you set it to automatic, the software automatically select which of the three main net identifier modes to use. So either global, everything can be connected, either you are using ports of sheet connector or net labels, everything will connect with everything as long as they have the same designator or the same net name or same port name. Now this is for the global. So basically the automatic mode will make a decision based on three options. If there are no sheet entries and no boards, the software will automatically select the global. Now, if there are sheet entries on a top sheet, the software will automatically select the hierarchical. Now, if there are no sheet entries, but there are boards present, then the software will automatically select the flat mode, which make all the sense. Okay, so let's go back to the slides. And now we need to start creating a multi-sheet design. So again, in a flat design, the connections between the sheets, different sheets, can be created by ports or can created by off-sheet connectors and or can created by net labels. Now the recommended approach is to use net labels within each schematic sheet and ports to connect between different schematic sheets, as we can see in here. Now, what is the difference between boards and off-sheet connector? Now, boards, they have more options, including the board cross-reference, where you can add a number on the board to refer to the connection with the other sheet. It will tell you the sheet number where this board is connecting. Let's say this sheet number, let's say 11, and this sheet number is 12. Now on this connector you will see number 11 in here, and on this connector you will see number 12, and this will tell you that this port is going to sheet number 12 and this port is connecting with sheet number 11. So this feature, or what it's called port cross reference, is not available when you use off-sheet connector. Off-sheet connector, it's like legacy, a comment or legacy component you can use in Altium Designer, but in all the time I prefer to go with the ports if I'm connecting sheet with sheet, and I go with net labels within the same sheets. And let's do one example for that. So let's go back to the project we created in here. So we have parent, we have child 1, we have child 2, and we need to do a flat design. So first we need to design with flat, and so let's create a new project, and let's save this one for the hierarchical design. So let's create new project, new project, create. So let's add 2 schematic sheet under this one, and we need to create a flat design without top sheet. We don't need a top sheet. And let's save this, save. Let's call this sheet 1, let's call it, let's give it as sheet 1 is okay. 2 as sheet 2, it's okay. And the project, it stays the same, okay. So now we have sheet 1 and we have sheet 2. Let's keep this docked in here so we can see what's going on. And let's add a component on sheet 1. Let's go to the manufacturer. Let's put, for instance, connector. And just for sake of doing an example, we need something simple. This is for position. We can use this one, place. It's loading. Okay, so let's add it in here. And now, so let's add ground and connect this with the ground, and also add VCC. This is an external connector, let's say, and this one and this one we need to connect them through a board. So we can take a board, place it in here, and we need another one. And now same thing, take the wire, connect this one with the board. You see the red cross telling you it's electrical connection connecting with another electrical connections. And now you need to change the name of this one. Double click on it. Let's say this one is A2, and it's, let's say it's bidirectional, and this one is A3 and it's bidirectional. So we are done on the first page. Now we need to do the same connector on the other page, and it's like we have 2 connectors to connect it together. So it's similar to if we do this. So if they are connected like that or like that, so without boards, but we need to put this on the other sheet. We can go in here, and now we put this sheet in here, and now basically if we tools, annotate schematic, let's convert this to the layout, execute, and we have done this process before. So now everything is connected. Save. Now let's add a layout to this so we can see these connections, the physical connection on the layout. Now let's go back. So let's compile this project first. So the project is compiled. As you can see, these are the nets we have. We have 2 components. We have G1. If you double click on it, it will be selected. We have G1 and we have G2 as well. And we have 4 nets. We have GND. We have net G1 underscore A2. Basically, the naming scheme in Altium Designer, they say name, then the designator underscore the bin name. This is how Altium Designer do the naming, unless if we come in here and add a net label to this. And to add a net label, basically either you can click on it and place net label, or you can go into the wire in here, select net label, and you add it. Now let's change this net label. Let's say this is A2 and this is A3. Now let's compile the project and look what will happen in here. Compile. Now if they are changed. So this will tell you the priority Altium Designer used to name the nets. So basically, if you have a board, it will not, the Altium Designer will automatically name the nets based on the default naming scheme. Now, if you have net label placed over the net, you are forcing the software to use your net label name rather than using the default naming scheme. And this is one of the important points. So now you can see more meaningful name for you to understand what's going on in this net. Now let's transfer this design into the layout. Cannot locate. Okay, let's save everything. Save the layout. Okay, now let's send the design, execute, and connect the sheet, and this is the second connector. And here you can see we have two connectors, and the name of bin number 4 is ground. If you go back, so bin number 4 is ground, bin number 1 is VCC, number 2 is called A2, number 3 is called A3. So here number 4 is ground, number 1 is VCC, number 2 is called A2, number 3 is called A3, and this is the net label will have the same name. And to see the net label name, you can go to PCB, all nets, and here are the nets. This is A2, this is A3, this is the ground, and this is the VCC. And this is how the flat architecture work. So basically everything will be connected through just ports. And look, we don't have here yet a top level sheet, but you can add top level sheet into this one. And here we have sheet 3, and let's save this one as and call this one, let's call it top level. You can name it anything, but let's call it top level. And now you go and place a sheet symbol and another sheet symbol. And now you can name this one, let's name this one child 1, and assign sheet 1 to it. And then this one is called child 2, and assign sheet 2 to it. Now you can combine the project. You can see you have a top level. You know that this is a top level sheet, and this is sheet number 1, and this is sheet number 2, but you don't have any entries, any sheet entries in here. You don't have any boards, and basically the two sheets are connected directly with these ports, nothing else. And this architecture is still called flat. It's called flat. And what is the reason for having top level sheet like that? It's just telling you that you have sheet number 1, and this sheet number 1 is for X function, and sheet number 2 is for Y function, and stuff like that. So just reference for you. If you have like 5-6 sheets, then you know that I have sheet for LCD, I have sheet for power, I have sheet for microcontroller, and so on. Now it makes sense if you have more than 5 or 6 schematic sheet to go into the hierarchical design, not stay with the flat design, because it provides more meaningful architecture for the user. Now let's go back to the slide. So how we can add board cross-reference. Now let's go to this. So let's save this, and let's save everything in here. So let's go to add board reference. Basically, if you look at these boards, now all that you know is this connecting with any boards. You might have 100 schematic sheets. So let's add one more just to show the benefits of the references, and add schematic, and let's call this schematic sheet 3, and let's add also another connector to it. Okay, and let's tool annotate, because new component. Okay, and now let's go back to the top level and add one more child, and now this will be called child 3. You need to make sure that you have a unique designator, and then this will be linked to sheet number 3. Now let's compile the project, and now you have still flat, and you have this is just the top level, and you have all these underneath it. Now, in order to have for the software to tell you, okay, this port is going to sheet number 2 and sheet number 3 or sheet number 1 or sheet number 100, all that you need to do is to go into report, port cross-reference, add to project. Now you can see that something added into here, and same thing in here, same thing in here. And you can see that you only see a reference, a grid reference, but you don't see the sheet name. Why is that? If we look at the sheet number, the sheets are not yet numbered, and that's why we are not seeing the sheet number. What you want to do, you want to go into tools, annotate, and then we need to number the schematic sheets. And here, let's sort it like that, and let's move this to the top, and or keep it down, auto numbering, update, okay. And now we can see there should be numbering on that. And let's regenerate the boards. Let's try to remove it again and remove from project. Let's save the project because it will not show if you don't compile the project. Now report, cross-reference, add to project. Yep, that's it. So here you can see that number 2 and 3, this is telling you this is sheet number 1, and this is telling that this port is going to sheet number 2 and sheet number 3, and the here between parentheses you can see a grid reference, but you don't really care about the grid reference. But what you can do, go to the preferences and under schematic general, and here you have port cross-reference. So location style, I don't need the location style. You can specify XY location on the sheet or the zone. I don't care about it. What I care about is the sheet style. I need the number. So what you need to do now, go again, report, remove it from the project, and report, add it to the project again. And now you can only see number 2 and 3. So this is telling you that this one is going to sheet number 2 and 3. If you open schematic sheet 2, it will tell you it's going to 1 and 3 because all of them are connected together, and this one is going to 1 and 2. And the other option you can do, instead of number, you can say the name. Basically, you will get the sheet name instead of the number, but again, you need to regenerate the reference. Now it will tell you this one is going to sheet number 1. Let's say you named sheet number 1 as MCU. So now you will see that it will tell you this one is going to the MCU or going to the LCD and so on. So they are very handy when it comes to flat design like that. But they are not useful when you talk about hierarchical design. So this is the first part of it, which is creating flat design with port cross-reference. So we learned how to do that, and it's very simple. Now the second part we need to do is creating hierarchical design. So for hierarchical design, you have two options to do that. And before we do that, let's re-talk a little bit about this design. So the hierarchical design has two major strengths. The first one is the ability to show the reader the functionality of the design in the way that the schematic sheets have been structured and presented as logical blocks. So this is very, very handy, and this is what you can see actually in here when we look at the mini PCB samples provided by Altium. So if you look at the big structure, you know what's going on. You have a full or abstract understanding of the design. You know that you have an FPGA, you have memories, you have peripherals on interfaces, and you have power, you have connectivity, and you have ROMs and so on. So you get a full overview about the design. And now if I want to go into, for instance, into the Ethernet interface, all that I need to go is open the module dedicated for the Ethernet and modify anything I want or reuse that design. This is one of the strengths of that design. You get a full understanding at high abstract level of the design. So that's the top level schematic here present the design as a set of high level functional blocks. And that's all you need at the first glance. And these blocks can be further broken into smaller blocks if needed, as you can see in here. For instance, the power block, if we go into it, it's broken into smaller blocks to show the distribution of the power. So your input is basically 12 volt, 16 amp is going in here. And now this one is broken into different power supplies and different rails, power rails. And the same thing in here for the FPGA chip. Now it's starting breaking into different interfaces. And this will allow the low level schematic to carry a components and low count of components that's relatively simple and can be reused, and also it make it easy for the review. And the other advantage now when it comes to printing this schematic, now if you print it on a paper, if you look at this one, it's very easy to understand and see it on paper. But if you have everything on one sheet, it's really difficult to print it out. There is no way you can print it out, and there is no way you can track the traces on it. And the other advantage of hierarchical design, it's easy to trace a signal through the design, because the engineer just need to match sheet entry on the parent sheet to another port on the child sheet, as you can see here, to track the traces and the signal as well. For instance, here on the FPGA, you know that this is DDR4 for the memory. This is the address and control clock. So you have address, control, and the clock signal going from here to here, and here also the same thing. If you get into this sub-circuit, you can see the address, control, and the clock connected over this harness, and you can easily track it back where it goes on the FPGA chip. And it's very easy to track it. But if you have everything connected together, you have hundreds and hundreds of nets you need to differentiate between. So always try to use hierarchical design, because it provides reusability and simplicity of your design and make it readable by any designer or user or engineer. So let's now try to create a hierarchical design, starting with top-down design methodology. So you have two different design methodologies. The first one is called top-down, and basically you start in top-down. Basically, you start by creating the parent, and then from the parent you create the children's. The bottom-up design methodology, basically you start by creating the children's, then you create the parent and link all the children's into that parent. So let's start with the top-down design methodology first. So, and there is a tool or command in Altium Designer will help you with both methodologies or both architecture. So the first methodology, if you go to the design menu, there is a command called create sheet from sheet symbol. Basically, if you create a sheet symbol on a parent sheet, and now if you use this command, Altium Designer will automatically create schematic sheets and add the boards inside these sheets for you. So let's do that. So let's close this. Let me close this project. And let's close this project as well. So maybe we can, let's create a new project and keep this project as well. So new project. Okay, create. So now let's add one sheet, and this is the parent. This is going to be the parent. Let's change the template for this sheet, and it's design templates, general templates. Yet let's use the letter template from Altium Designer. Okay. So this is a literal template. Now let's save the project and the sheets. Let's call this PA. Okay. So let's save it. Okay. Now what we need to do now is let's add schematic symbol, and we need another one, and let's create one more. And remember, in hierarchical design, you not only have symbols, but also you need to have ports connecting these symbols together. Now let's add a port on the first one. Oh, sorry, sheet entry on the first one, and let's have this, and let's call this one as what did we call it on, because we are going to copy this connector, so A2 and A3. Okay, so let's call this A2 and this one A3, and let's select both, hold shift down and select both, and go to the properties and set them as bidirectional. Now you have several options. The first option is you can select a wire, and if you try to route, when you come to the side of it, just click on it and the board will be created with the same name. This is very simple. Or basically you can copy and paste the board and this will work as well. So let's now also so copy and paste. Let's try copy and paste. Basically you can copy it in here and copy in here. We are connecting A2 to A3. Okay, so A3. Oh, let's change the name for these. Let's name this just to change it, let's name this A4. I don't want everything to be connected together, and let's make this A4 as well. So we have first connector connect with the first schematic sheet and the second connect the second schematic sheet with the third. So what you need to do next is to go select these, and now you only have the parent in here. Go to the design, create sheet from sheet symbol, and now you get this cursor. Click on the sheet and you see a sheet created for you, and you can see the boards automatically placed inside the sheet. So go back to the parent, design, show me a sheet for this. Oh, and let's save this sheet. Let's name this sheet. Let's call this child 2. Parents, design, create sheet. Now let's name this one. Let's name it. This is child 1. And let's go back, design. Need this one, Control S. And this is child 3. Now you might say, oh, it's just 2 boards, it's not huge, but remember the motherboard samples we opened where you have so many ports you need to connect? Now this will become handy in this case. Now we have only 2 just for sake for example in here. So let's place the same connector now we had, and all that we need is to connect this port to the connector. Same thing, but now we have hierarchical design instead. So now on these now are called, we can change them into A4 and A5. Now in the, we will talk about it in a second. Let's do the rest. Okay, so copy here. Okay, it's A2 and A3. Child number 1. Also I want A3. I don't need this. This is from the old project. Now let's go back to the parent and try to link these. And this goes into child 1, this goes into child 2, and this goes into child 3. Okay, now let's save it. Now let's annotate the schematic. Okay, execute, and let's number the sheets as well. And we have, okay, we can get this number 1, number 2, 3. Okay, now let's compile the project. Okay, so we can see children 1, 2, 3. Let's save it. Now let's try to compile. Says unique identifier error, and A2 looks like when we did the copy and paste, we have problem with the ID. If you came across problem like that, what you can do, the easiest way to solve it, if you go to tools, convert, reset component unique IDs, and select reset duplicates, and okay. Oh, we have one update, yes. So for, okay, we have schematic object. Okay, that makes sense now. And let's compile. Okay, solved. Okay, so this is how you can solve it if you come across a problem like that. So it's compiled successfully and everything is connected now. This is good. So we have the first child. Basically, we have a connector. Let's add a label in here, and let's call this one A3. Now, this label has nothing to do with the labels on the other sheets. You can have the same name. Let me show you. And here, and they will not connect together. And this is A3. Okay, on the other one, and compile. Oh, the duplicate net name. Oh, it's, yeah, the compiler will give you a warning, but they are not connected together. Even if you change the name. Yes, duplicate. Okay. So now let's add layout to this project, and we need to save it in order to be able to send the changes to it. So we have saving. Okay, so we have child 1, we have one connector. So if you go to the parent, so on the child 1 we have one connector connecting with child 2. We have two connectors in here. So the first connector goes to child 1 and the second connector goes to child 3. So if you go to the top level, we are done with this. It's parent in here. This is child 3. So on this one we have two connectors. One goes into child 1 and one goes into child 3. And child 3, of course, you only have one connector. Now let's transfer design, update, and we don't want to generate the rooms. We don't care about the rooms for now. Oh, designator already exists. Okay, we need to do the designators. Reset, how you can solve it. Also, you can reset the designator and you can annotate the schematic again. Okay, close, copy, save. Okay, design, update. We don't need this. Okay, we have G4, connect G3, and G1 is connecting with G2. Okay, so we have child 1 is connecting with child 2, and on child 2 also we have another connection is connecting with child 3. And as you can see, the ground and VCC, these are power ports and they are global. It doesn't matter even if you go to the project option and change this one to hierarchical design and stay global. The power ports are always global, as you can see in here. So they are global. And if you look at the net names in this case, all nets, so you have A2, and you have A3, and you have A4, and you have A5, and these are the nets. And then you have ground, and you have the VCC. So this is the first one, which is top bottom. We started from the parent, we created these children in here, and then we generated the sheets for that parent. So the second method is bottom up. Basically, you start from the children and then you build the parents based on that. And there is a comment for that called create sheet symbol from sheets. So let's check it out very fast. So let's assume that this doesn't exist. Let's remove it. And in this case, we have these children, but we don't have anything on the parent, and we need to build that structure. So what you need to do, you go into design, create sheet symbol, which is the one we want to create, the sheet symbol in here. Design, instead of doing that manually, Altium Designer can generate that for us from sheet. Now when you click on this one, Altium will ask you which sheet, schematic sheet, you want to create sheet symbol for. We select child 1. Now you place it in here. As you can see, the boards came up automatically, and you have the name exactly that the designator for this sheet is called child 1, and this one inherited from the schematic sheet name. And now same thing we do for the other two. We select, we need the second one, and on the second sheet, if you open the second sheet, we have 2 connectors and we have 4 ports, and these 4 ports came into here, but of course you need to reorganize these ports. Now we need this port on the other side, and we need these ports on this side. You can just reorganize them. And then we need the third sheet now. So design, we need the third one, and this one will come in here. And all that you need to do right now is just to connect these ports together. Just select the wire, connect the first one to the second one. And this is a faster way. Now, again, this is just 2 boards. Imagine that you have the huge project in here. Let's open reset project. So we have the mini board, and here. So you have all these connections, and you need to build. And instead of doing that, Altium Designer will build all that for you. So Altium Designer will place these ports, and you don't have to worry about it, and you just need to connect, and that's it. You are done with that. So now we can compile this project, and let's see, we have unique identifier error for some reason. Let's see, Altium tool. So we can solve it as we did in a second. So just reset. Okay. Now tools, annotate, reset schematic designator, and we can annotate again. Execute. Okay. Done. Messages, no problem at all. Yeah, for some reason when we use these comments, create sheet from symbol or create sheet symbol from sheets, the ID, the unique ID, because each object has a unique ID in Altium Designer, and if you use the same unique ID or you use the same designator, Altium Designer will show an error. So when using these comments, for some reason the ID is getting copied, and this is not allowed. I need to talk to Altium about it, and this is like a bug or something if I'm not mistaken. So anyway, so this is the second method where you do a bottom-up design methodology. So what next? Okay, so moving subcircuits between sheets. Also, this is a command that is very useful in Altium Designer. And usually, if you go, let's go to Altium Designer. Usually in Altium Designer, let's say I want to copy this connector with all these reference into a different sheet. So when I do a copy, look what will happen to the designator. Let's say I'm copying this one. So let's take this one to the parent. I can put components on the parents, that's fine. Now look what happened. Now the designator, we lose the designator. Now it's not the designator. What if I wanna copy components and keep the designator, the same designator without any change? Let's say I wanna copy let's say USB 3 here. For instance, this circuit in here. I want to copy all these and keep these designator the same designator, or I want to move these into a different sheet. Let's say I want to take this out from here and everything from here. I want to take it out and Control X. I'm just cutting everything and I want to move to, let's create new sheet in here and new schematic, and I want to place all of them in here. Let's Control V. Oh, it doesn't fit. Let me change the template, use a bigger sheet. Design, templates, general templates, and let's use A3. Okay. Oh, it's changing everything. That's a problem now. I used the wrong command, but it's okay. Basically, I changed the template for all sheets. I should change it only for the new one I created, but that's fine. Okay. So let's paste what we covered in here and look what will happen. Now we lost all the designators. We need to re-annotate this again, and if we have this component already placed on the layout, we will have problem now. So even for the caps, everything is gone. So how we can fix this? So let's go back. So how we can fix this? So let me close this project because we changed a lot of things. I don't want to lose it. So it's closing. Let's wait until it's closed. There is delay for some reason. Okay, good. So how can I copy these? That's one I want to copy these into this parent. What can I do about it? Now there is a command you can use. It's called edit, refactor, move selected subcircuit to different sheets. When you use this command, the Altium Designer will copy everything without resetting the unique identifier in each component. So when I do edit and refactor, move selected subcircuit to a different sheet. Now Altium will ask, where do you want to move them? Let's move them to the parent. You can do that. Now here is the parent. If I put them in the parent in here, as you can see, they still have their unique identifier. And this is useful if you are at the design stage and you started creating schematic sheets and sub sheets, and you are designing, and then you decided to move some components from one sub schematic sheet into another. So this is how you can do it without losing the unique identifier or unique designator. So the next is the cross-probing and selecting. Now these are very important. Basically, cross-probing feature is accessed from either the schematic or the PCB editor. You can cross-probe both ways. You can cross-probe in the layout and see the corresponding components, net, pin, and the schematic, and the other way around as well. Now, when you cross-probe an object, either component or bin or a net, in either schematic or layout, the target document will display the corresponding object in accordance with the timing options defined in the system navigation page of the preference dialog. So let's see how we can change that and how we can work it out. So let's open a project. Let's open the same project we had. Oh, it's okay. So let's open the layout, and we need to close all these because we need to split the screen, have a half for schematic and half for the layout, because I'm only recording one screen right now. But if you have two monitors on your desktop, you can use one for the schematic and one for the layout, and you can cross probe and cross select between the two. And this is very important when you design a PCB to have two big monitor screens. So I usually use a 32-inch by 32-inch 32-inch, two monitor 32-inch when I do a design, PCB design. So now let's close these. Yes, close, yes. Let's close this one as well. So let's say we need to have, let me open DDR4. Okay. Now what you need to do, if you have one screen, you can tilt vertically. So now you need to go into tools and cross probe in here, or you can find cross probe also on the toolbar in here. So now if you cross probe in schematic, let's wait, it's loading. Okay, so let's say you can cross probe the components in here, and basically let's show not manufacturer, needs visualization. Oh, I need to select the layout. Okay, so if you go view configuration, and I need to see that top and button components. Okay. Okay. Oops. Yeah. So this is the IC. We crossed probe in here. Now let's go back to the command. Okay. And here, click on the schematic. Make sure to select the schematic if you are probing from schematic, and let's probe a net. So this net. And you can see now the net. And let's probe now a bin instead of a net. You click on the bin. You can see it in here. This is the bin. It's B3, and this one is, take the net name DDR4 underscore A0, DDR4 underscore A0. So let's probe a component again. So as you can see, everything here is dimmed. So how we can control this options? Basically, you go to the preferences in here, and you go to system, and there is navigation, and under the navigation here you can control how far you get close when you select a component or you cross probe component, and also you can control the dimming. Is it invisible everything or not? So let's say I don't want to get very close, so let's change the settings right now like that, and here it's not so close and everything is not dim, so you can control that from here. Okay, so this is for the cross probe, and this is very useful when you do testing or trying to check the connections, and you can do the same thing on the schematic or the layout as well. So if you, let's say, this is cross selection, so if you click on select the layout, for instance, and you select, okay, cross probe, and let's probe this bin. You see the schematic also will be selected and the bin will be selected in here, and this is G7, as you can see. So it's bidirectional both ways. So the other one is a cross selection. For cross selection, basically cross probe, you just probe that object. For selection, you can select a component, but this is the same thing as cross probe. But here, what you can do, you can select multiple components at the same time. Oh, because okay. So because the nets are selected in here, you won't be able to see anything because you have a ground, and the ground is everywhere. So if you want to select component, basically you can go to the properties and say I want to only select components, and now you have the filter on and you select these components, and here we go. So you selected the memories, the power for these memories, and you have the decoupling capacitors around them. So this is the selection, cross selection. And also this works both ways. So you can select a component in here and you will see it on the schematic as well. And also this is very useful feature, because if you open something and I have a connector or something, so where is this connector, Ethernet connector located? I can click on it, or I can see it right now in here. Now, what if, let's say if we click on this connector in here, let me change the properties, is all objects, okay, and top overlay, let's double click. Oh, okay, so when I select this component, I still cannot see it because the sheet where this component is located is not open. So what can I do in this case? Right click on it and select cross probe, and look what will happen right now. So basically Altium Designer open the corresponding schematic sheet where this component exists for you if it's not open. Okay, so this is for the cross probe, and yeah, we are done with that. So toggle net color override, also this is very useful feature you can count on, as you can see this in this example, and this is courtesy of Altium. I got this picture from Altium website, and you can toggle net color override in using F5 short key, and basically to help bring clarity and visibility, the designer can apply color to the schematic wiring or the PCB connection lines and routing, and this will be very helpful to track the traces location and differentiate between powers and data and clock and so on. As you can see in here, for instance, we have the first half of the data bus, the first 8-bit. As you can see, they are color coded with blue, and then you have the second part is color coded with yellow, and then you have another connection color coded with red, and then magenta, and so on. And now you can see these in here. So how we can do this coloring thing? So on this project, I think they already have colors implemented into it. So if you select, let's view all the layers in here, and if we click on F5, you see how the color is changing now. F5. So let's take the layers one by one, and maybe we can see it on the power. And ground, we don't need the ground. Let's take the ground out. The ground is solid color. And take the ground and this ground as well. And let's take the top out. And maybe this layer. So this is a signal. We don't need the power. Let's take this power as well. So you see how they color coded these traces. You can see that. So these basically are colored in the layout, or let's see if they are colored in the schematic. So no, they are colored. Oh yeah, in the schematic. So how you can create these net colors? It's very easy. All that you need to do is you go to Here you have these tools with net color, let's say fuchsia for instance, and let's say you just click on the wire. So let's say this is fuchsia and everything in here I need it to be colored in fuchsia. And now if we click on this, this is the wire, and let's show the layer. So many layers. I should have selected the assembler project to show the colors. Or maybe we can select our symbol project to show it, because this will take a long time. Okay, so let's go back to the project we created in here. Didn't we save it? Oh, okay. So we need to move these to chart number 2, annotate, quickly. Then let's commit changes automatically. Okay, here are the connectors. Rules. Do we have any? Okay, errors. Okay, let's hide the component and mechanical layer. I just want to see the traces. Okay, now let's route these and let's make it wide so we can see it. Okay. Oh, okay. It's restricted. Let's design rules, width, and allow maximum width of 100. Okay, now this is showing error. Looks like, oh, okay, that's why. Okay, so let's have this align with this, and now let's route these. Okay, these are going all together. Just for demonstration purpose, we are routing all of them on one layer. Or maybe we can put this on the bottom layer. It's okay. Let me change this to the bottom layer just to see the difference in color. So now all of the nets have the same color, or the layer color. So if you look at the configuration, so the top layer is red, the bottom layer is blue. Now let's go back in here and let's say this is parents. Let's say this color in here. Let's go and give this one fuchsia, and let's give this light blue, and this yellow, and the other one dark green. We basically change the color, and if you get inside the children's, you can see that the children's inherited the coloring, net coloring from the parent, because they have the same net and the same name. Now all that you need to get these changes into the layout is you need to compile and update. Now you can see that we don't need to add rooms. it's telling you that this net color has changed to this color. And let's commit that. Okay, and here you go. And if you click on F5, you get the default coloring based on what you have in here. Of course, you can change the color in here for this layer. But if you click on F5, now you can see the net color defined in the schematic, as you can see in here. So we can change also the color for the power as well. Now, how we can change the color for this power line? You can go to the PCB and select the nets, and now you have a VCC. Now we are doing the other way around. Now you can go into change net color, and I want to use, let's say, this color for the power. And when you click on it, now you change the color for it. And for ground, let's say we want to change the net color into this color, and it's changed. So now can we commit these changes in here in the color for the power, for the ground and VCC into schematic? Yes, you can go into the design and say update schematic. Instead of import change, you can update schematic. And yes, so it will say this color will be changed on the VCC and GND. So execute. And now if you go to the schematic, and if you go into the children's, you can see the color on it. And look at the VCC, so it's bi-directional as well. And this is very handy as well if you have so many nets. If you have a data bus and you need to separate, differentiate high voltage traces from low voltage traces, you need to look at the low clock signal, for instance, and so on. This will be very handy as in here. So from the color, you know that this is a data bus for DDRAM1, this is a data bus for DDRAM2. These are differential signals, and these are high-speed signals based on the coloring scheme. Of course, you are not limited to the color palette available in here, because you can do a custom color. So you have unlimited number of colors to color your signal. Okay, so this is for the coloring, and we talked about applying color to schematic net, how we can do that. You can do it from view, set net color, or you can count on the toolbar. And the other way around, we did also apply color in the layout net. From the layout, you just go to the PCB panel, select the net, and click on that color. So now we need to talk a bit about design synchronization. Basically, design synchronization is performed directly between the schematic and the PCB editors. The software will use like a smart comparator engine to compare all the aspects of the design, detailing the output as a list of differences. Then the designer needs to decide which side should change to resolve the differences. As we saw a little bit when we changed the color, we were able to commit the changes from the schematic to the layout, and then we did some changes on the layout, and also we were able to commit these changes on the other way around, backward. Now, whenever you try to commit changes, an engineering change order or something called ECO will be created. These are then applied, bringing the two sides of the design back in sync. So between the schematic and the layout, and you will see something called ECO. Engineering change order, as you can see in here, and the engine will tell you, okay, these are the differences, and this is the old one, and this is the new one. This is what will happen, and you need to confirm that. And all the time you need to make sure that your schematic and layout editors are synced, and there is no difference between the two all the time. And there is bidirectional tools in Altium Designer that shows and update if there are differences. Basically, you can go into a project, and there is show differences. And this show differences, you select this is the schematic, and you select the layout in here, and it will show if there are any differences. So you can see there are no differences between the two. Yeah, and if there are differences, you can commit these differences very easily. So this is just a quick word about it, because this is very critical. Sometimes an engineer might change something on the schematic and forget to commit that to the layout and release the layout board without committing the change of the schematic. And then when it comes to implementation and testing, oh, there is a big problem because one of the nets was changed on the schematic but was not committed to the layout, and it's not right. So there is discontinuity between the schematic and the layout because they are not synchronized. So before you generate your fabrication files, make sure, try to check if the schematic and layout are synchronized and there is no differences. Even in sometimes you are working on the layout and by accident you delete a net or a component. So if you don't check the sync between the schematic and layout, you will never know that there is a problem actually. So one of the verification steps is to check that both schematic and layouts are synchronized. Navigator, this is the last slide in today's session. Navigator is a good method to review the component, the connection between the components, the nets, the bins, and so on. If you go to the schematic and click on, this is simple. We should open much complex design, but you can see that you have a parent director, parent sheet, and you have child 1. You double click on it, it will take you to child, then child 2 and child 3. And on child 2 you have 2 connectors, and on the first connector, these are the parameters for the connectors, as you can see. And also you have another connector parameters, and here are the signals. You can see the signals. You have A5, A4, A3, A2, VCC, and the ground. For A5, you can see what pins this net is connected to. Is connected with G3, which is connector G3, pin A3, and this pin is defined as a passive pin in the library of this component. And then you see the net labels. We have 2 net labels created. It's A4 and A5, or A4 for this pin, and these are connected to port A5, as you can see. So you get very detailed hierarchy of how these pins are labeled and connected and so on. So this is the navigator, and it's good to review what components and how they are connected. And that's all for today, and thank you a lot. One more session and we can close this course. So the next session we will try to build 4-layer PCB and 6-layer PCBs. We will talk about planes, power planes, and how we do stitching for the via, and try to apply all the concepts we learned over the 10 sessions. So the next session, session number 11, is gonna be the last session in this series. After that, we will start a new series for signal integrity in depth. We'll talk about signal integrity, EMI, ASD, EMC, design concepts, and we'll move forward from that. Crosstalk, differential pairs, differential signals, and data buses, and so on. So thank you all, and talk to you in the next session.